We are surrounded by moving objects every day, and velocity plays a key role in understanding and predicting that motion. This lab measures an object traveling at a constant velocity, that is, an object moving at the same speed without changing direction. The observed motion of this object will be measured and then compared to a computational model to see how well predictions of motion are to what is observed. The results show that there is a weak correlation between the predicted and observed measurements. The observed average velocity had an x component around negative 0.1687 meters per second, while the predicted average velocity had an x component of negative 0.0661 meters per second. In order to look at constant velocity, Newton's second law is needed. This law states that a force is applied on a system when there are interactions between objects. By focusing on one system, all the interactions being applied to that system can be added up to equal one net force. This net force can tell a lot about a system, and in order for the force to change, there needs to be a change in the interactions, such as in velocity. In this lab, the goal is to apply force to an object with constant velocity. This means that the velocity is not changing, and therefore the net force being applied to the object should be zero. This lab uses a board of wood as a flat surface to ensure that the gravitational force is balanced by the surface during the whole duration of the experiment. So the y component of the velocity vector is 0. An aluminum can was used since its shape ensures the direction of the object would not change, so the z component of the velocity vector is 0. The x component of the velocity vector should be the only non-zero number now, so a constant velocity in reality is more attainable. Using Tracker, the video of the object traveling with constant velocity along the x-axis was able to be measured. The video consists of the aluminum can moving along the flat surface as well as a ruler to determine its appropriate length. The center of mass of the object is indicated by the red dot in each frame as it moves in the negative x direction. The corresponding table and graph shows the relationship of position versus time. The initial position of the object is located at negative 0.0055 meters. The total change in time for the system is 3.5037 seconds. The initial velocity can be calculated from taking the change in position from the first two data points divided by the change in time for that duration. The initial velocity is calculated to be negative 0.0661 meters per second. By calculating this initial velocity and comparing it to Newton's second law, the initial velocity should be equal to the constant velocity for the system. GlowScript is used to determine the predicted measurements for our system. The mass, initial position, initial velocity, time interval, total time, and net force vectors need to be specified for measurements in the observations. In order for GlowScript to predict the measurements of the object, Newton's second law equation must be rewritten to be solved for final velocity. Since the net force is 0, final and initial velocity are the same, and the code is now predicting an object's motion based on constant velocity. The last thing that needs to be edited for in the code is the final position formula. The velocity formula can be rewritten so that the final position is being solved for. This allows for GlowScript to plug in the other values of the initial position plus the average velocity, which in this case is constant, times the change in time for the prediction. When the code is run, a model, graph, and table is given which shows the predicted positions for where the aluminum can should be traveling at a constant velocity. The blue dots represent the observed data, while the red line represents the predicted values if the can had a constant velocity. As pictured, the two do not line up, and since the predicted model strictly follows Newton's second law, it can be concluded that the observed data did not travel at a constant velocity and therefore had net forces acting on it. To try and improve the observed results, a different surface could be used. While the board was level and flat, a smoother surface would have allowed for the object to travel more constantly without the extra momentum after going over a small bump. Another thing that could have been taken into account in the future would be to use an empty can. This way, there won't be liquid splashing around to mess with the can traveling at a constant velocity. If the axes were to be flipped, the numerical velocity calculated would be the same, but the velocity vector would be different. Instead of the x component being a non-zero number, whichever axis that the object was moving along, the corresponding component would also change. If it was being measured along the y-axis, for example, then the y-axis would hold the non-zero velocity, while the x and z components would remain 0. It is not possible to say how many pushes and pulls are added together to give the zero net force in the observed case. There could be many forces acting on an object, such as gravity, air, friction, and even more interactions that are invisible to the eye. What is important in measuring forces is not the individual impact of each interaction, but the net force.